Hi friends, I am Ramesh Chandran. In the last class, we studied about atom, charge, voltage, current flow, etc. I hope that class might have been useful to you. If so, please like it. Also, comment it so that I can correct it and give you in a better way. In this class, we will be studying about what are the factors that affects the value of a resistance. Also, we will study about different combinations of resistances. The value of resistance depends mainly on two factors. One is length of the conductor and another one area of cross section. To understand this, take the case of two rods. One is a narrow rod and another one a wider road. We know that in narrow roads traffic jam will be there, vehicles are moving very slowly due to that obstruction. Also, when more distance vehicles have to move, the time taken also will be more. In the case of wider roads like highways, obstruction will be less so that vehicles can freely move. Similar is the case of resistance also. When length of a conductor is increasing, the resistance also will increase. In other ways, we can say that resistance is directly proportional to length of the conductor. While taking the area of cross section, resistance is inversely proportional to area of cross section. That is R is proportional to 1 by A. Combining both, we can see that R is proportional to L by A. Take two conductors, one copper and the other aluminium. Both are having same length and same cross sectional area. But if we see the resistance across the two ends, they are having different resistance. That means there is a third thing which controls resistance of the materials. This is due to one property of these conductors called resistivity. Good conductors are having low resistivity while insulators are having high resistivity. Resistivity is denoted by the letter rho and its unit is ohm meter. So, we have seen that R is proportional to L by A, that is R is equal to a constant into L by A. Here that constant is resistivity of the material rho, so R can be written as R is equal to rho into L by A, where rho is the resistivity of the material, L length and A area of cross section. Value of resistivity also depends upon the temperature of the conductor. See this example. A conducting wire has a resistance of 5 ohm. What is the resistance of another wire of the same material but having half the diameter and 4 times the length? Let R1 is the resistance of the first wire and L1 A1 its length and area of cross section. Similarly, let R2 be the resistance of the second wire and L2 A2 its length and area of cross section. As both are of the same material, rho is same for both. We know that area of cross section A is equal to pi d squared by 4, as diameter d2 of second material is half that of the first. d2 is equal to d1 by 2, or d1 is equal to 2d2. Therefore, A1, area of cross section of first material, A1 is equal to pi into d1 square by 4, that is equal to pi into, we know that d1 is equal to 2d2. So substituting here, A1 is equal to pi into 2d2 the whole square divided by 4, that is equal to pi into 4 d2 square by 4. The common factors can be cancelled, so A1 becomes pi d2 square. Considering the second material, A2 is equal to pi into d2 square by 4. Therefore, A1 by A2 is equal to pi d2 square divided by pi d2 square by 4, that is equal to pi d2 square into 4 by pi d2 square. Cancelling these common factors, this becomes 4. So A1 by A2 is equal to 4. It is also given as L2 is 4 times L1, that is L2 is equal to 4 L1. Bringing L1 to left hand side, L2 by L1 is equal to 4. Therefore, R2 by R1 is equal to rho into L2 by A2 divided by rho into L1 by A1, that is equal to rho by rho into L2 by A2 into A1 by L1. By cancelling common factors, rho and rho goes, so that this becomes L2 into A1 divided by L1 into A2, that is L2 by L1 into A1 by A2. You have seen that L2 by L1 is 4 and A1 by A2 is also 4, so that this can be written as 4 into 4, that is 16. Therefore, R2 is equal to 16 R1, that is equal to 16 into 5, which is given, that is equal to 80 ohm. So R2 is 80 ohms. See, in this figure we can see a combination of resistance. We are seeing R1 and R2, they are connected one after the other. If seeing this junction, it is seen that three resistances are connected to a common point, while here R5 and R6 are connected like two parallel lines, while in this one you can see three resistances R3, R4 and R5 connected as a triangle. Here R7, R8 and R9 also comes to a common point. So to understand what are these type of connections and to simplify this type of connections, we will study one by one. See, in this figure, three resistances R1, R2 and R3 are connected one after the other. This is called a series combination of resistance. This resistance is connected across a voltage source V. These three resistances connected in series can be shown as a single resistance Rs. So V is the voltage. As per the value of this voltage and depending upon the value of resistances, a current will be flowing through it. You can see that the current flowing through these resistances will be the same in all the three resistances, while the voltage depends upon the value of resistances. Here total resistance V is equal to V1 plus V2 plus V3. Here V is equal to I into Rs. V1 is equal to I into R1. V2 is equal to I into R2. V3 is equal to I into. Therefore, this equation can be written as I into Rs is equal to I into R1 plus I into R2 plus I into R3, that is equal to I into R1 plus R2 plus R3. Removing the common factor I from both sides, we can write as Rs is equal to R1 plus R2 plus R3. That is when three resistances R1, R2 and R3 are connected in series. The total resistance in series will be Rs is equal to R1 plus R2 plus R3, the sum of the three resistances. Now see this example. When three resistances 22 ohm, 150 ohm and 470 ohm are connected in series between A and B, calculate the total resistance between A and B. As the resistances are in series, total resistance is equal to R is equal to R1 plus R2 plus R3. That is, resistance between A and B is equal to 22 plus 150 plus 470, which gives 642 ohm. Now see in this figure, three resistances R1, R2 and R3 connected like parallel lines. This type of connection is called a parallel connection of resistances. A voltage is applied across these resistances. This voltage and this combination of resistances R1, R2, R3 causes a current I to flow through it. When R1, R2, R3 are connected in parallel, it gives a value Rp. So the current flowing will be equal to I is equal to V divided by resistance, V by Rp. So that current is coming here from this junction. It divides into 3. How much it is dividing depends upon the value of the resistances. In this case, voltage across the three resistances will be same, but current will be different depending upon the value of resistances. As the total current I entering in the junction divides into I1, I2, I3, I can be written as I1 plus I2 plus I3. From here, I is equal to V by Rp. As the voltage across the three resistances are equal, I1 is equal to V by R1, I2 is equal to V by R2, I3 is equal to V by R3, and here I is equal to V by Rp, that is total effective resistance. Therefore it can be written as V by Rp is equal to V by R1 plus V by R2 plus V by R3, that is equal to V is a common factor, 1 by R1 plus 1 by R2 plus 1 by R3. From left hand side and right hand side, cancelling the common factors V, the equation can be written as 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Voltage divider concept is very useful in analyzing circuits. Consider two resistors connected in series one by one across a voltage of V. Here current is same through both resistances, but voltages divided as per the value of that resistances, and total resistance between these 2 points are R1 plus R2. I is equal to V by the total resistance. I is equal to V by R, that is equal to V by R1 plus R2. If V1 is voltage across R1 and V2 is voltage across R2, we can write V1 is equal to I into R1, that is equal to V by R1 plus R2 into R1, or V1 is equal to that is the voltage across R1. V into R1 divided by R1 plus R2, that is voltage across R1. V1 is equal to total voltage V into R1 divided by sum of the two resistances. Similarly, V2 is equal to V into R2 divided by R1 plus R2. Voltage appearing across a particular resistance is total voltage into ratio of that resistance to total resistance. Like voltage divider, current divider is also useful in analyzing circuits. Here two resistances R1 and R2 are connected in parallel and a voltage of V is applied so that a current I flows through it. This current I divides into two. It is I1, I2. So current through R1 is I1, current through R2 is I2. Therefore, V is equal to I1 into R1 and V is equal to I2 into R2, or I2 is equal to V by R2, that is equal to I1 into R1 divided by R2. But total current I is equal to I1 plus I2, that is I1 plus I1 R1 divided by R2. Therefore, I is equal to bringing this to this side, I1 is equal to I into R2 divided by R1 plus R2. Like this, I2 is equal to I into R1 divided by R1 plus R2. That is, in current divider, current through R1 is equal to total current into R2 divided by R1 plus R2. Similarly, current through R2 is equal to I into R1 divided by R1 plus R2. So friends, I think this video might have been useful to you. If so, please like it, share it, subscribe by pushing that bell button so that you will get all the new video notifications. Thank you for watching.